All right, so hypothesis tests can be a bit of a mystery at first, but they essentially set up two possibilities. One's called the null hypothesis possibility, and the other one's the alternative hypothesis. And we put all our focus on the null hypothesis one. And then if the data don't really support that, then we kind of conclude on the alternative hypothesis. So let's take a look here. We have a knee surgery, and we have an 8-week recovery time. But now there's this new physical therapy style proposed, and they say that the mean is less than 8 weeks, so it's going to improve on the current method. We have some data from a sample, and we know that for the sample, the mean recovery time is less than 8, but we can't yet conclude that in general, this new physical therapy will be less than 8. Because there's always sampling error, and we have to make sure it's low enough that it's really likely that in general this type of therapy method would actually be lowering the mean below eight weeks. So that's why we're doing the test. We're seeing, not for this sample. We know for this sample it worked out great. What we want to know is, are the results convincing enough from this sample that we can believe it in general? Okay, so that's why we're going to perform a hypothesis test. We start off by working with the null and alternative. So a couple tips. The null should always include an equal sign. So let's grab our equal sign here. And we're dealing with the population mean. Now, we know what the sample mean is. So the null is about the population mean. And we think that it's, if nothing's going on, null means nothing, then this would just be equal to 8 weeks here. So the null hypothesis, null means nothing. That means if this surgery isn't effective, or if it doesn't really lower it below 8, then what's our mean going to be? Now you might argue that it could be greater than or equal to 8, but I think really mathematically, let's just stick with the null always being an equal sign, because that pins us into a very specific distribution. So just always go equal sign in the null. Now in the alternative, once you've got the null, you've actually got two parts. The mean, it's going to be the same. Whatever parameter you're testing here is going to be the same down here. And the number is always going to be the same. So really the only decision you have to make is on the sign. And here we're trying to say that the mean recovery time is less than. So you're looking for some kind of directional word. And here we have less than. So again, the other two parts are going to just mimic the null hypothesis. But our alternative would be if our data doesn't seem to think that the null hypothesis is the right conclusion, then we're going to settle on the alternative. And again, the greater than is kind of built into the null. This is considered a one-tailed test. So we're really only able to reject the null in this left direction if we think the mean is less than 8. Okay, perform the hypothesis test. So here's where we need to calculate a z-test statistic, and we're doing a z because we know the population standard deviation, or we're assuming that. If we didn't know that, we'd be doing the same process but with a t distribution instead of a z. Okay, so it's one-tailed. This is matching this less than. Another option would be greater than. That would also be one-tailed. Another option is not equal to. That would be a two-tail. We could reject because it's low, or we could reject because it's high. That would be a two-tailed. But we just have one. Our critical value here is based on z.10, and we can just pull that from the calculator here. So that's going to give us 1.282. And what that means is that's the target. I think of it as like a basketball shot. We're gonna calculate our z-test statistic, and if we make it into this zone we're able to reject the null. We have statistical significance. We have evidence for that claim. Okay, so the test statistic, we're going to have to calculate this. So let's grab our calculator. And we have the, oops, put myself over here. Okay, so we have a fraction, really, but I'll just do it like this. So our sample mean was 7.6 minus, this is our null hypothesis mean, which we can see right there is 8. And then we're going to divide that by the standard deviation, which is 2.4. And that itself is getting divided by the square root of the sample size, which is 35, and we will put that in square root. Okay, and this is going to give us z of negative 0.986. Okay, pop myself back over here. So did we actually get in there? Did we get into that zone? Well, we were over here. Oh, and this is, okay, I wondered why we were setting this up here. So we need to do a left-tailed test. That's what we were checking at. So the only way we're going to reject is if we're far enough over in the left tail. So we need actually the negative version of this. There we go. So in order to reject the null, our alternative was that our mean is going to be less than 8. And so that's why we had to flip this here to put it on the left side instead of the right side. And our test statistic was not inside that, we call it the rejection region. It was not low enough to convincingly reject the null hypothesis. So since we do not lie in the rejection region, the null hypothesis is not rejected, and that means there's not enough evidence to support this claim. So yes, our sample mean was indeed lower. It was 7.6, which is great. Maybe there's some chance for this new method, but it wasn't a strong enough result. Here is where we would have had to been to be convincingly sure that this new method is actually lowering the average for everyone, not just for this sample below 8.